convention alpha. Significance level is represented by the symbol alpha, Greek alphabet alpha. Alpha will correspond to 0.05. Generally, for any type of tail test, for two tail, since it is a symmetrical one, half of that 0.05, that is 0.025 will be on the lower tail, 0.025 will be on the upper tail. So sum will be 0.05 always. Everybody has understood this one. Huh? It is not, that is not exactly equal to 2, less than 2. It will be 1.96. If you try to trace it out along with the Z table, the shaded portion for the two tail ones, it will be Z values corresponding to 1.96 on either side. And for one tail, it will correspond to somewhere around 1.64. That also we'll see in the next one. This was another question for you to do yesterday. I hope all of you have tried. If you want to cross check your answers, the answers are given here. Accuracy and precision we learned long back, maybe in the second or third lecture. And yesterday's class, the day before yesterday, we had discussed that when we have a choice to do in between systematic and random errors, the one which has got lower random error, that is better precision, we will keep it as the better candidate, because systematic errors anyway we can control. That is a key to answer this one. And the 4 curves in the increasing order of precision, just by looking at the curve, the width of the curve we can do, or else you can go for the sigma square values. The sigma square is variance, nothing but the square of the standard deviation. You can see the numerical value and do assessment, or you can look at the curves and take a decision. Both will lead to the same. When mu is equal to 0, that means your value is sitting on the true value. When mu is equal to -2, that means there is a bias, negative bias. My value is some -2 units away from the true value. Is this clear to all of you, these questions? If I ask you to do similar way, maybe similar pattern, I hope all of you will be able to do. Systematic error, random error, then the increasing or decreasing order of precision, you can make comment on those things. No? Till now, whatever we have discussed is the continuous probability function, wherein all the expressions were following the Gaussian distribution. Echo आ रहा है क्या आप लोगों को? Are you getting echo? Echo हो रहा है क्या? थोड़ा सा आवाज कम कर लीजिए. थोड़ा सा कम कर लीजिए. General nature of random variables is that Gaussian distribution function, wherein we see the resultant as a bell shape. It is not that always you land up in the bell-shaped random variables only. Sometimes you may have sometimes you may have rectangular distribution or triangular distribution, sometimes skewed distributions also. Those are not mentioned here. It may not be always symmetrical. There may be some tailing, extension of tail or towards the lower part or the upper part, maybe some flattening of the peak. Those are the real practical experiences. We will see 3 cases. One is the regular one, normal probability distribution function. Then the second one is rectangular distribution, which says that the probability of getting any value on equal distance from the center point is same. Then you will have a flat distribution. The probability is maximum, or whatever be the value, the same probability, equal probability, then sharply decreasing. When you move from that particular distance, there is a sharp decrement in the probability. It is a bit imaginative, but this type of observations are found when we do the measurements of volume using, say, not calibrated measuring devices, or the measuring cylinders or beakers or buckets or larger volume containers. This type of observations are found practically. Rectangular type of distribution. This is one of the extreme case of this random variable distribution, you get the same probability for any value at a particular distance from the center value. Okay. Another one is that instead of exponentially decreasing on either side symmetrically, it may be linearly coming down in like in the fashion forming a triangle with the peak on the center. This is another case. For example, you have semi-calibrated measuring equipments or volumetric class. In laboratory practice, you might have seen that class A, class B, like that measuring equipments are classified. Class A measuring equipments, they come under their measurements will lead to rectangular, Gaussian, normal type of distribution. If at all the measuring device is not in the class A, it is in the secondary class, class B, then you will see the repeated measurements using such devices will lead to the third one, triangular type of distribution. Okay. So how to calculate the mean variance are given here. If at all you happen to have similar type of observation during your measurements, if you have the probability of any data falling on either side as equal, then you presume that it follows a rectangular distribution. Then instead of calculating the standard deviation and variance directly, you can use this formula. If the distance from the center point is say d, the deviation is d and the variance will be d square by 3. There are derivations to these variances that we are not doing here in the class. And for the triangular type of distribution, where you will be using these different ones, if at all, in a particular set of experiments. If you are using a measuring cylinder, then the volume measured by this measuring cylinder, you have to anticipate that the variations during the measurements may be of this type. The variance when you are calculating, we have learned absolute variances are additive during addition or subtraction, relative variances are additive when we do multiplication or division. There we have to calculate the variance, isn't it? For calculating the variance, you have to use these equations. There are many more different types of distributions pertaining to continuous variables. We are restricting to only 3. There are different skewed type of distributions, unsymmetrical distributions. Sometimes you will have intermittent vacancies, blank, like the different various type of distributions are there. These are the most commonly encountered when we do research. Yes. D is the distance of your value to the measured value. We have calculated error, x minus mu. It is D. The point, D is the distance of your value. Here we are not using the word standard deviation. Here we use the D. Standard deviation. Standard means there is something, there is some particular protocol which is to be followed when you are doing a standard. When I say there is a standard for this class, there is some criteria which we have like we have already crossed. Whereas here we use only the term deviation. Standard this first prefix is deleted because in rectangular distribution the variations are not predictable and the distance d is not defined. Wherever you are standing, from there it will be. When you say standard curve, standard probability curve, we have taken the difference with respect to the base sigma. We have taken z curve, then we have taken z curve. We have divided x minus mu with sigma, isn't it? Then we had plotted z curve. We had a base. We had a reference value. Here there is no reference value, so the word deviation, D is used. That is the only difference. And standard deviation, yes. Variance is the term like which will guide me through to calculate the errors whenever I am doing mathematical operations. That is why this variance term is required for us for calculation. This is derived from the area under the curve. Each of these d square by 3, d square by 9, d square by 6. These can be derived from the area under the curve corresponding to that particular distance from the center point or the peak point. Here also these two distributions which we are learning today, the triangular and rectangular, they are also symmetric distributions. We are not going to asymmetric distribution. Till now, whatever we have discussed were continuous variables. In the first class, we have defined variables as two different categories, one as discrete, another one as continuous. Discrete ones are those which are countable, which have integer values. For example, the number of students in this room. If I ask what is the height of each of you, then it will be a continuous variable. Number, integer numbers, they will be discrete. So till now we have learned insert table, random variables, all those come under continuous variable functions. But if you this one is for you to have a comprehensive idea regarding the entire type of variables. We will not go much deeper into discrete variables, discrete probability distribution. Very rarely we encounter such type of distributions. Then we do statistical analysis because most of the time we address continuous variables. This is for those of you who may be doing, for example, radioactivity measurement. For them, the radioactivity generated will be following this second type of discrete probability distribution, Poisson distribution. This is one example I can anticipate for you to deal with during your research, this Poisson type of distribution. So only for those cases in practical, I have also used this discrete probability distribution. Binomial and Bernoulli functions already we have learned. Whoever has learned mathematics in 11th and 12th, you might have used this equation. We will not go to the derivation. We will use only the required terms like mean and variance. We require mean for representing the average value, variance for doing the propagation of the error. And how the variable is defined. These are the only things we require for statistical analysis. And here the terms in these all equations, n is the number of trials or the number of counts or whatever parameter we are doing, what are the independent quantities, number of quantities. Then P is the probability of getting whatever target we are looking for, probability of getting that target back, that is probability of success. Then the Px will be the predicted probability for such success. And for Poisson distribution, there is another term called lambda, which is defined by the product of n and p. Binomial is a general function. This once you apply some conditions, it becomes Poisson distribution. And another set of conditions, binomial can be restricted to Bernoulli type of distribution. Whoever is using in future this type of distribution, for them, one simple example I have given so that you get a grip of this different type of distributions. Binomial, Poisson and Bernoulli distribution. You need not have to by heart the equation. Just understand how the calculation is done directly using the equation. I'll show you the question and come back to this slide so that you get to have a feel. Here turn to if I have to find out what is the probability of getting two tools defect among 10 such tools. Here all are in integers. There are no fractions. So out of 10, 2 tools are defective. You are counting the number of tools. Here in this case, we can apply discrete probability function. You can use either binomial or Poisson distribution and calculate. Either of the two equations given in the center of the table. For those of you who want to do the calculation will be like this. For exam, all of you are allowed to bring the calculators. You can bring your calculators after erasing the memory if anything is stored in the memory. Clear the memory and bring. And try to have your own calculators. Sometimes they may not allow you to borrow your friend's calculator. This is simply substitution in the equation. Relevant equation we can substitute. So since there are some restriction or boundary conditions applied in the Poisson distribution, you see there is a marginal difference in the probability calculation. Instead of 0.19 in the general case, you get 0.18 for the case of Poisson distribution. These slides will be available to all of you. Then you can have a check later on. So till now, whatever we have learned where the standard significant figures, rounding off, place value, error propagation, then this thing, normal probability distribution function, then we could conclude whether the manufacturer his claim was right or not. We could take this decisions. So for taking such decisions, initially we propose that whatever be the number of manufactured electrodes, all of them will have same light. That is my initial proposition. That means whatever be the experiment I do, I will land up in the correct result. But may not be the true all the time. No? So you will have random variation. Initially, we propose that we reach up to this level. We will fetch the degree in 5 years. Some of us may be doing it faster. Some of us may be taking a few more time. So like that, there may be random distribution. So if you are testing the reliability of a particular set of measurements, initially we say that all the results obtained by a set of people, all of them are correct and all of them are up to the mark, all of them are reaching the true value, which is almost a hypothesis. So it means rarest chance. We had seen that when z is equal to 0, the probability of getting that value is almost near to 0. It is like that only. But however, initially we have confidence we propose like that. Everything will be all right. We will do the things in the proper way. But ultimately, when you complete the experiments, you realize that it is not the case all the time. Initially, we proposed that our value, measured value, is exactly matched. It will be matching to the true value. And finally, after getting the results, we see that there is a deviation. Then what we do, we propose a hypothesis that this and this are true. These are equal. By a Z test, we have seen that they are like almost same, almost within a belt of Z is equal to plus or minus 1 or plus or minus 2. In that case, if it is Z is equal to plus or minus 2, that means we are 95.4% confident that our value is exactly matching with the true value. That will be our hypothesis. Our value is matching, and with 95.4% confidence, we are telling that yes, we have achieved the target. And sometimes, due to random variations, this your confidence level may swing from 95.4 to may sometimes 68.3 or sometimes even lower. Our idea is to reach like till date the consensus is that whatever result we propose, that will be agreeing with the true value with 95.4% confidence. If not, we will apply some modification in the procedure and try to improve the procedure and get better quality result. And if at all, now we use the term confidence level. If in terms of significance level, if you talk, we try to minimize the significance band below 5%. That is less than 0.05 in fraction if we say. I'll not read through the text, whatever is written here. Whatever it is conveyed that we discuss. So initially when we do, like when we are going to assess a property of a material, initially we say that yeah, this material is suitable for a particular application. Initially we always have a positive attitude. Then after evaluating, it may so happen that it qualifies, sometimes it may not. So depending on that one, if at all it is qualifying, we say that the initial my proposition, which we call as hypothesis. And initially we were blind, we are not aware of regarding the property. So we say that it is the null hypothesis. We have nothing in hand, but we have hypothesized that this is same as the, like whatever we are anticipating. Okay. Once you feel that you are not reaching up to the level, then we slightly modify our statement. I was not targeting this one. I was targeting something else. So I propose alternatively. Then, then we say that null hypothesis is rejected. That is one way of stating. Another one is that alternative hypothesis is standing. So these are the ways of like presenting. Rather than I got rejected from this particular interview, I will say that I am eligible for something else. That is a positive way of presenting. Even if I get a negative data, I will say that this particular material or this particular procedure is suitable for some other application, rather than saying that it is not qualifying. That is a better way of presentation. And confidence level and significance level we have defined. Confidence level is the level or percentage of the total area under the curve corresponding to particular level of cell. And 1 minus that, when you say in fraction, that is significance level, we represent that as alpha. So if you know the confidence level, definitely significance level you can calculate. Or the other way around. Okay. This is the null and alternative hypothesis. Initially we start that 2 or more data points, they are identical. That is the initial null hypothesis. If we say we have one mu and one mu 0, they are same. If the null hypothesis is not standing, not correct, then we propose that we have an alternative way of telling it. Mu is not equal to mu 0. Another way of telling. And if at all there may be an upper tailed distribution which we are relying upon to compare, then we say that mu is greater than mu 0. That will be one way of alternative hypothesis where the proposed value is larger or bigger than the actual value. Significantly larger. Or if it is significantly smaller or lower than the true value, then we use the lower one tail of representation shading, and we say that the proposed mu is smaller than mu 0. These are the different ways of making it presentable, making the data presentable. So from this example, all of you will be able to understand whatever we have discussed in the previous slide. For example, if we are determining whether the concentration of lead in an industrial water is exceeding some limit of 0.05 ppm. If it is exceeding, if I say exceeding, it is always on the higher side. So it will represent an upper tail distribution. Alternative hypothesis will be that mu is greater than that mu 0. Here it is 0.05 ppm. So this way, when you are doing statistical analysis anytime, for that matter Z or any other statistical parameter you are evaluating, you will first propose what you are going to do. Null hypothesis is the first step. Then if at all you find that null hypothesis is not standing, then you go via the alternative hypothesis. Without changing the statement of null hypothesis, you will say that alternative hypothesis is valid in this particular case. Here in the first example one, we use the upper tail of the hypothesis testing. That is why greater than symbol is there, mu greater than some particular value. If it is lower tail, mu less than some particular value, like that. If it is either greater or lower, then use two-tailed curve. This we have seen in the utilization of Z graph as well as Z table also. This is another way of representing the same thing. Are you people getting bored or saturated? Saturated? आज पूजा हो गया क्या इसीलिए? You want to take a break of 5 minutes or what? Or should we continue and wind up fast? अच्छा एक कंटिन्यू करने के लिए बोलते अभी मैंने. And everybody wants to continue only. Okay. So whenever you are super saturated, you tell me, I will stop. Huh? Are you all super saturated now? Or shall we go ahead a bit more? Because I will be meeting you only once in Friday again. That will be my last class. Friday will be my last class. Friday. इसका exam somewhere in the end of October. Total marks 50 last this thing. End of October. Research methodology, research and publication ethics. These are the two courses clubbed together. These are around 12 lectures. Last online lectures, we had exam for 40 marks from the statistics part. 10 marks from the Atindra Sir's part, research methodology. And the research and publication ethics, that is a separate exam. That was for 100 marks. Total is 150. Kalar sir and Atindra sir ka research publication ethics 50-50 each. Mine will be 40. And in this one, whatever we discuss in the class, based on that one, numericals will be there, true or false, sometimes match the following like that. On Friday, we will have just a recap of the entire thing. And if time is there, we will have some sample discussions. So you get to know regard, or you may be getting the question papers also, I think. Like reference, previous online exam was there. I don't know whether it is available in public. Whatever we have discussed during the significance figures, rounding off, error propagation, all those things will be useful, and different types of representation. From that you can make comment regarding whether it is accurate, precise, or which one is having more error, less error, like that. Judgmental. Nothing descriptive. I normally do not give descriptive ones. Multiple choice questions will be there. Like if I ask you to find Partition area corresponding to this particular result, if the Z table is given, all of you may be able to read through the table and do. Na? If I ask you to calculate what is the probability corresponding to so and so Z to so and so region, Z equal to minus 0.6, Z is equal to plus 1.6, like that. Randomly I can ask. You be comfortable how to read the Z table. Today, if possible, we will go to the other statistical test, t-test. Let us see. So now that you might have seen this figure, yesterday also similar figure we had seen while discussing the said normal probability distribution. Here you can see that lower portion is shaded with black lines, which corresponds to an Z value of 1.6 less than 1.645. If you calculate if you refer to the table, the corresponding area to the shaded one will be 5% of the total one, 0.05 in fraction. That means 95% of the area is not shaded. 5% is shaded. Now that we are going to discuss significance level, that is a tail portion, lower tail portion, it is shaded here. And normally when we propose the hypothesis as this value is same as the mu zero, then whatever is beyond, whatever is not a part of the tail, that is in the agreeing with the null hypothesis. That means it is acceptable as per the null hypothesis. That is why in blue font it is written that acceptance region, which is not shaded. The shaded region will be the rejection region, which aligns with the alternative hypothesis. Similarly, if you have an upper tail, the same explanation holds. Here one mistake is there in the figure. It is written as z equal to minus 1.645. Like just it should be plus 1.645 on the right side figure. If it is a symmetrical two-tailed curve, symmetrically half of that alpha will be distributed on either side. For the first and third figures, it was 0.05 of the entire area. Now 0.025 on the lower part, 0.025 on the upper part, summing up to 0.05. Okay. This is a general convention for like any of the statistical hypothesis testing as of today, keeping alpha as 5%, significance level as 5%, if at all not mentioned explicitly. That means z equal to 2. Confidence level 95%. These are the different ways of doing the hypothesis testing. One is that we can say my value is matching with the true value, or my value is away from specific threshold or lower than the specific threshold. Sometimes it may so happen that we want the value to be higher than, larger than the threshold. If I am preparing a catalyst to enhance a reaction, then always my target will be to have the value larger than the threshold. But if at all it is a poison like lead or arsenic in drinking water, then we will say that lead the value should be less than the threshold value. It all depends on the case or context. So first you have to read through what you are looking for. Whether your value is expected to have swing on either side, or you are anticipating only one-sided result. If you are anticipating only one-sided result, you will go for one-tailed test. If you are not sure whether it will be one or two-tailed, go for two-tailed test. If there is uncertainty, if there is no surety, or if you want to like confirm your value before presenting it to another person, you can have cross check with your friend or labmate or other instrument like that. Between two means measured means you can do the comparison. There also you can use the hypothesis testing, get yourself convinced that you are right, you are in the right direction. That is another way of doing the hypothesis test. So in order to do any test, you have to have some procedure. You should explicitly state the steps. What are the steps involved in? What are the steps involved in the calculation? Then finally, you will state the null hypothesis and your conclusion, whether your measured parameters are aligning with the null hypothesis or not aligning. Alternative way of telling will be, I am deviating from this one and I am targeting something else. These are the way. If the calculated value is less than the threshold value or the critical value, then we say that null hypothesis is valid. If not, then we go along with the alternative hypothesis. We have seen that when we were using Z table, we have used the population mean mu, population standard deviation sigma. But many times this sigma may not be available, like we may not be aware regarding what is the value of sigma. And sometimes it may so happen that we may have limited time to do the experiment. We may be doing some 2-3 repeated measurements, or rather 5 or 6 repeated measurements. Then if you try to plot them, it may not properly give you a bell-shaped curve. If you have 5 or 6 data points, it will be difficult, extremely difficult to mimic that bell-shaped curve. You will have some other asymmetric distribution. One such distribution is t-distribution. That is one more practical than the Z distribution. If you have limited number of data points, if you have less than say 30 number of data points, we had seen already while doing the calculation of standard deviation, the denominator was modified by n minus 1 instead of n. Similarly, in the case of asymmetric distribution or tailed distribution, actually distribution has got rather big or larger tail compared to the Z distribution. We will see one figure. If you people are bored, then we will just have a comparison between T and Z and stop there. Give you some exam like work to do at home. Tomorrow you have a holiday, na? So let us try to wind up. Time is there, only 3:20. T distribution function is more or less same as the Z distribution function. Only difference is that it is applied. T distribution is more applicable when you have lower number of data points. That will be the real life case. And the population standard deviation is not known. Whatever we have done, the sample standard deviation is only in my hand. I am unaware of the population standard deviation. So it is more or truly realistic when we do in day to day, unless you have large number of data points. Otherwise, it is the mathematical expression. If you see, Z was also equal to x minus mu by sigma. Here T is x minus mu by S. Okay. This mu can be x bar also. X minus x bar by S also is possible. T distribution is utilized for comparing our value with the population mean or the two values, my value and your value, x minus x bar or x1 bar minus x2 bar. Like that, numerator can be modified accordingly. There is flexibility. And the denominator is always standard deviation S. And when we are comparing two means in the numerator, denominator automatically gets modified. S by root of n1 for particular mean x1 bar, and if at all there is another mean, s by root of n2. Accordingly, the situation slightly gets modified. S by root n comes from the error propagation for mean. Here we have limited number of data points when we are calculating the t value. So when the number of data points are limited and are interrelated by their mean, the variables required to define such data points that we call as degrees of freedom. This may be a new term for you, degrees of freedom. Degrees of freedom is the minimum number of variables or functions required to define a particular property or a particular material or a particular quantity. Here, when we have limited number of measurements and they are interrelated through their mean, their degrees of freedom will be the number of measured properties minus 1, n minus 1. That will be the degrees of freedom. In the case of wizard table, this parameter was not required because we were always dealing with large number of data points. Degrees of freedom, this does not matter in that case. Here, this parameter has got a major role. As you increase the degrees of freedom, the t values will have some change or alignment. That figure I'll show you, then you will be able to appreciate. And when I say t value, I have to define what is the degrees of freedom and what is the level of significance. When we were saying z is equal to 2, then degrees of freedom was not required because we were dealing with large number of data points. And we say that z equal to 2 corresponds to 95.4% confidence level. Here what we use is degrees of freedom and significance level rather than confidence level. We are rather looking at the tail portion of the curve. When we were looking the Z table, we had seen the portion as the one which is closer to the center point. Here in the case of T table, we will be focusing on the tail portion. That is why in the previous curve, the tail portions were rather more shaded rather than the center ones. Though it was for Z calculation. And confidence interval, when we are using T statistic, it will be x bar plus or minus Ts by root n if we are taking the mean of certain function. This is a like a typical T table. Now let us try to understand how this table we can read through. similar to the Z table, we have a leftmost column, then there are some bifurcations between the top 2-3 rows and the rest of the columns. You can see that the leftmost column say that CUN.PROB, that is cumulative probability. Cumulative probability corresponding to particular values of T, we are going to read. And under that it is written one tail, two tail. Which type of test we are going to apply? Whether we are going to use it as the null hypothesis as one is greater than the other one. That is one case, or one is less than, very much less than the other one. That is, though in those cases, we have to use the one tail wala one. And if you say that the value may be either greater or lower than the other one, then we use a two-tail type of distribution. Now underneath that it is written DF, that is degrees of freedom. Okay. And in the T table, degrees of freedom is defined as number of data points minus 1, n minus 1. When you come down in that column, 1, 2, 3, 4, 5, 6 like that, the values are given up to very large number up to 1000. Whereas in the case of Z table, we had seen fractional values 0 up to 3.4, 3.5, 3.6 like that. Only up to 3.4 only yesterday I showed. Up to 3.6 only those are tabulated. But whereas T table values are even tabulated beyond this large one. And when you are going towards the right, wherein you have the cumulative probability or area under the curve, on the right hand side, the area values which we use for the corresponding region, shaded region, you can see on the right side, like a second column on top, it is written T.50, isn't it? T.50. Then below that 0.51, like that it is written. So it corresponds, T.50 corresponds to certain level of alpha, significance level. Whenever you see a subscript beside T, it will be for certain significance level. Okay. And ideally, it should also mention what is the degree of freedom. So degrees of freedom, you can read from the column corresponding to that particular degree of freedom. You can read the value. You have to ensure which number, which type of evaluation you are doing, whether you are doing greater, less, or equal to, not equal to, like that. If it is either greater or less, then you go for one tail. If it is not equal to, you go for two tail. Okay. Just by stating, it may not be like, you may not be getting the feel. Na? We'll try to do, and T values are written with significance level as subscript. If you are comfortable reading through the confidence level values are written on the last row. On the last row, it is for you in this type of, as we have seen in Z table also, there are different types of representation. In T table also, there are different types of representation. Some of the tables, they give only one-tailed value with a certain significance level. They do not mention the confidence level. Sometimes they give two-tailed values. Definitely, in their this thing, title or note, they will mention what type of distribution they are expressing. And this is the simplest one, wherein you get significance level as well as confidence level. So you can have cross check. If I write significance level of 0.05, which will correspond to confidence level of 95. So 95% is the one, 1, 2, 3, 4, 5, fifth from the right. So when you are expressing the T value, it will have a subscript of degree of freedom and the significance level of significance. T critical, degree of freedom, and alpha. So if I ask you what is the T2 and 0.25 for one-tailed T distribution. For degree of freedom of 2, and a significance level of 0.75. T 0.75 for 2 degrees of freedom. Anybody can tell me what is the area cumulative probability? Degree of freedom is 2. They have come down 2 rows. Now 0.25 in the one tail. What will be the value? 0.816. Now you have understood. If I ask you any random combination of degree of freedom and significance level, you will be able to do. Na? Keep in mind the degree of freedom is one number less than the total number of measured data. That is one point you have to be very careful while assessing t values. While doing the calculation of t from n set of measurements, if it is n such measurements and you have taken mean, x minus mu divided by s by root n, that n remains number of data points. But when you are looking for the degrees of freedom for t, that time you have to see for n minus 1. Whereas the equation for t does not change. Equation for t, the denominator for s by root n, that remains as such. This one-sided and two-sided test we do depending on the context, whether you are looking for a value which is above certain threshold or whether it is not agreeing with the other one. The whatever text is written on the lower portion is for you to get familiarized how to read through the T table. For example, if I ask you to read for one-tailed T for a certain degree of freedom and significance level can be expressed as fraction or percentage. These are the two ways, either as fraction or percentage. Here in this case, significance level is written as fraction 0.05 and 5 degrees of freedom. So this way you can read through. You have to choose whether you are going for one tail or two tail. Accordingly, you can read through the table. Okay. So you can see that when the significance levels are half, we have already seen that for two-tailed distribution, the alpha significance level is equally half on either side. So if I am looking at a particular degree of freedom, for a particular specific degree of freedom, if you increase the significance level to double, then two-tailed value will be equal to that of the one-tailed value. Okay. Be careful which context you are looking for, two-tail or one-tail. So when to use T, when to use Z. Yesterday we learned Z table. Today we are going to learn T table. When we have sigma known, then we go for Z table. When sigma is not known, I am not sure whether this is actually sigma or standard deviation from my friend, then I go for T test. That will be the more practical case. If sigma is known to us, then you use the normal distribution table Z. If sigma is not known, we go for the T distribution. And when the number of data points are less, the preference will be using the T table, which will be the more realistic case. And the confidence intervals also already we have learned how it is expressed. The same thing is written here, when to use Z table, when to use T table. When the number of data points are very large, that means you can almost get the uniform distribution of the data points. The table can be used provided sigma is known to us. Normal probability distribution, wherever it is applicable, Z can be used. If you are in confusion, then go for T table. The different types of paired or independent type of T tables that we will learn further. This is the curve I was talking about. There are around the 1, 2, 3, 4 curves are there. Among these 4, the green one which has got the last peak and smaller tail portion. If you compare the green curve with the rest of the curves, you can make out that green one has got the highest, has got the peak. Shapes are almost similar, more or less similar, and the green curve has got lower tail portion area. If you compare the area covered by the tail portion starting from say -3 to infinity and +3 to infinity, green has got the smallest area. When you go from green to yellow to blue to purple or purple, then you see that your tail portion is increasing, getting elevated, and at the same time, the peak maximum position probability is decreasing. That means more and more data points are moving away from the center point. Tail portion is getting filled up. That will ultimately land up in T type of distribution. Original green one was my Z type of distribution, normal probability distribution. When you see the tailing is enhanced or increased, that is the real case, practical case, that time Z curve is not applicable, then we have to use T table. And the other way around also you can say, if you increase the number of data points from purple to blue to yellow to green, you can achieve. Our target will be to like reach up to the green type of distribution. That will be a symmetrical with a narrow width of the baseline. That will be our target. For that, what we have to do? We have to increase the degrees of freedom. Degrees of freedom is almost like number of measurement. In the Z table and T table also, if you have the both the tables compare like on the same slide, you can see that at the infinity, T value in the next slide I will show you the T table. T value becomes almost equal to that of the Z value when you are increasing the number of data points. And standard deviation also will go on like getting closer to the population standard deviation. So yes, gets slowly replaced with the sigma. That is why we are asked to do repeated measurements by our guide while doing the experiment. One thing is to confirm our data. Another thing is to get the natural variable, natural property as it is in our laboratory. Whatever is there, get the like exact map of the variable or the property. This you understood. Now, when the degrees of freedom increases, T value becomes closer and closer to the Z value. That is why in the case of T, we have been mentioning large number of degrees of freedom. In the case of Z, degrees of freedom had no role because it is independent of the number of data points. Presumption, it started with large number of initial data. And these are the different cases where we apply t-test. T-test is applied for comparing our experimental value with a known or established value. If I am developing a new procedure or new method or some new compound I am synthesizing, if somebody else has done similar kind of job, I will check my proficiency or check my value by comparing this one with already existing, isn't it? When we start a new job, if at all there is already written a procedure is there, we will try to follow it first. Then whatever he or she is stating in the document, whether I am able to get that or not. And that time we use this test to compare whether I have reached the correct value or not. Not just by examining visually, we have to mathematically prove that yes, my values are in good agreement with the reported. So in these cases, the null hypothesis will be measured value is equal to the known value. Alternative hypothesis will be it is not equal to the mean value. When we have large number of data, we use the Z table. Null and alternative hypothesis will be like that. It can be equal to the true value, that will be the null hypothesis. Not equal to will be the alternative one. If it is one-tailed test greater than the true value, greater than the actual value, mu greater than mu zero, that will be one-tailed test. Mu less than mu zero, the alternative hypothesis corresponding to lower one-tailed test. Then we have large number of data points. This is almost replication of previous slides. Already we have discussed today. Then we have two-tailed distribution for comparison at 95% confidence level. Z is equal to 1.96 on either side. Beyond that portion will be shaded, which will correspond to equal significance level of 0.025 on either side. If we are looking for one-tailed test, it will be the Z value will be corresponding to 1.64 and the area will be 1.05. Yesterday's Z table, I'll show you that again. Lower one tail also will be applicable in the same way. So if you are calculating 95% confidence level for one-tailed Z table, it will be corresponding to 1.64. If you want to cross check with the Z table, which we have seen yesterday, 1.64. It is already marked with this pink circle. For one-tailed one. If it is two-tailed one, it is symmetrically distributed on either side. This particular type of distribution or graph is for one-tailed distribution with the shaded area corresponding to half the confidence level because upper half is only shaded. Already we have learned how to read this third table. Na? Shall we go ahead? When we have limited number of data points, till now whatever we have learned till yesterday, we learned the table. Today we have introduced another table, T table. Z is used when we have large number of data points and sigma is known. T is used when we have limited number of data points and sigma is not known. Accordingly, the equation also slightly gets modified. Instead of sigma, we will use S. Instead of sigma by root n, it will be S by root n. And we have to introduce what is the degrees of freedom when we are using T. And tailing test, like one tail or two tail, the null and alternative hypotheses are same here. When we are comparing two means, two experimentalist mean, here also you can use the t-test in same way. For example, if like two experimentalists A and B, they got some set of data points A curve and B curve. You can see the difference between A and B. Their peak points, mu A minus mu B, that we call as bias. If I take one, say mu of A as mu 0, then the bias will be mu B minus mu A, that is mu 0. That will be the bias. So here you can see that B has got a positive bias, isn't it? So such type of assessments and comments we can make using this comparison of these two curves. Just by seeing the curves, you can make out which one is having a bias. If at all one of them is taken as reference. If both are taken as comparative values, then there is another way of doing the assessment that we will see. Then when neither of them are considered as mu 0, then there is associated one equation that I will show you in the next one. We can compare the two means or we can take the difference between the two means. If the difference is very small, we can say that they agree with each other. If I ask you a question, if two of you give the same answer with slightly different like way of presentation, I'll say that both of your answers are correct. Different ways of presentation. Like that, if one value is derived by two different procedures or two experimentalists or two devices, we do the testing via the t statistic and see whether their difference is negligible or small. That way, whether the bias, in the previous slide we have seen the bias. Na? Bias is nothing but the difference between the measured value and the reference value. If I do not want to call the other one as reference value, if I say reference, the other one will feel that I am superior. Na? If I want to compare my data with my friend's data, if I call him or her value, his or her value as reference, they will feel I am superior to this one. Then another way of telling is that two values are being compared. None of them are being called as reference value. As long as sigma is not known, we never use the word reference. So you can compare two means either by taking the standard deviation, their standard deviation. If their standard deviations are similar, then we say that both of these are good performers, almost equivalent performers. If the standard deviations are visibly different, the one which has got a smaller standard deviation, we call it as better performer, isn't it? That is one way of assessment, standard deviation. Another one is agreement between these two values, mu1 and mu2. If their difference is very small, comparatively smaller than individual standard deviations, then we call them that their values are agreeable to each other. Both of them are qualified. This is another way of telling. For that also, everywhere we use the same t distribution function, same formula only we use. X bar minus mu, then we are referring to one value as reference value or the absolute value or the true value. These are the different terms for the reference value. Then we use the term mu. Instead of x1 bar minus x2 bar, we use x bar minus mu. The one is the reference value. Here, S will be the standard deviation which we obtained while calculating X bar. N is the number of measurements used for calculating X bar. Here, nothing is mentioned regarding the mu. Nothing in the sense standard deviation of mu or number of measurements for mu are not considered. When we have two means to compare, then we take the difference between the two means and then compare with the original value. Then in the denominator you see slightly it is modified. S1 by root of n1 and S2 by root of n1. Then you take the square and sum it. Then take the square root. Like in the it is not exactly the same as relative variance, but relative standard deviation is the standard deviation by the number of data points. Standard deviation by the number of data points. Square of standard deviation. You can say variance per number of data points are added up. And everywhere when you do that like mathematical operations, you keep in mind that either absolute variance or relative variance. These are additive terms. Variance is the property which is additive, whether it is absolute or relative. These are the different cases. If you people are saturated, I think you people are already super saturated. We will stop here. The next class we will start from here. Which are the different contexts we will apply this t statistic. This one we will start again because these are different cases. You may require some like fresh mind to understand this. This one we will start in the next class. This one let it be for like a homework for all of you. Will you be able to like pinpoint what will be the degree of like a t value for a certain confidence level and number of replicates? Number of measurements are given. So you have to read the degree of freedom as n minus 1. Yes. If it is 3, for example, one let us discuss the rest of the things you can do. For 3 replicate measurements, degree of freedom will be 2. And for a confidence level of 95, pardon? for a confidence level of 95%. It is not visible over there. Color, na? Okay. Numbers are small. Okay. Then I'll share this presentation with all of you. Like, I hope all of you are getting the slides. Then the DDFS, I got only one mail ID. I'm sending to that one, and the others I do in the group. You are also getting. I will share this one. If the table is not visible to all of you, just let us try to do only one. Confidence level of 95%. Can start from the lower part, 95%. What you can do is, you can have the values. Nowhere it is mentioned regarding it is two tail or single tail. Na? Then the obvious question will be whether it is for two tail or single tail. You can extend the table for two tail one, single tail one. Okay. Otherwise, if you are mentioning T critical for single tail, type T critical for single tail. All the single tail values you show. This slide I will share with you all. Try to arrive at these values. If you are comfortable, let us say for single tail values only we will. Okay. Once you know how to read a single tail, similarly two tail also will be. So all of you try to fill this table, degrees of freedom, significance level and T critical. Come with that data on Friday. I'll share this slide with you. Anybody requires any help to read the table? No, na? If not, we let us stop here. It is there in the downloads folder if anybody wants to do directly from here. Attendance sheet you give me. Give me the attendance sheet.